All right, thanks. So yeah, I promise I'm gonna try to keep this as short as I can and we can hold the lunch right after. So just to kind of go back for a second, take a step back. So we are doing what we said this morning, relating Legendrians to sheaf, Lagrangian fillings, gives you an object, Lagrangian filling with the local system. Now we're trying to focus a bit more on the space itself rather than the whole category. But remember that the geometric goal, as stated in the first lecture, was to actually just try to understand all possible fillings, Lagrangian fillings or Legendrian. And I kind of broke this down into 3 steps. The first one over there says just build as many fillings as possible. Because we have your lambda, and in all possible ways, just create as many candidates as possible. Now, there are different ways to do that. For instance, you can use concordances, concatenating with Legendrian loops and the like. But the method that I've been using in the last few years a lot is Lagrangian disk surgery. So this is something that was introduced by Leonid Polterovich in 1991, independently by Sikharov and Lalonde. But I'm going to tell you a bit about it, how that works. And the motivation is that using this method requires not just having a Lagrangian filling, but some additional data. There's going to be some Lagrangian disks in there. So we're not just going to want to find Lagrangian disks, Lagrangian fillings. We also want to find Lagrangian fillings with some extra data. And that's a self-compressing system that I'm going to tell you about in about 20 minutes. Now, once we've built all of them, step number 2 will be to distinguish them. Are they Hamiltonian isotopic or not? And here you will use sheaves. We will argue that these sheaves that we're going to build are sheaf quantizable, and we're actually going to give an explicit sheaf that quantizes these people. And now you want to tell them apart, and the computations look very much like my first lecture today, how then you start to use coordinates. Now there's a lot of ZIs floating around and a lot of things, so you want to have some method to organize that, and that's what the cluster coordinates do for you. They find good coordinates in these varieties that you can immediately tell things apart. And then step 3 is, well, everything we did above was actually everything there was to begin with. That is usually the hardest step in the sense that it is a step we currently do not know how to do, even for positive braid closures. So the first 2 steps for positive braid closures, I would say we're done, like we've really mastered that. And the next thing to do would be what happens if I don't have a positive, like some random like pretzel knot that is not a positive braid closure. The idea would be try to do steps 1 and 2 as well. Step 3, we only know it for the unknot and the hop fling, and that's it. So already for the trefoil, the candidates we will build, we do not know that we're not missing something. So a priori we might be, and that would be the most amazing paper. Somebody posts an archive paper that says the trefoil has 6 fillings. Just not really there. Okay, so Lagrangian disk surgery.
Roger, the hop bow, has that been written down?
It will hopefully be in the archive in the next month. It is written down, it's just not on the archive.
Okay.
We're going back and forth, so the student has written it down. All the math looked legit. Now it's sort of plus editing these pages. Okay, so what is this Lagrangian disk surgery? So the idea is the following. The idea is that given one Lagrangian filling, you want to build some other Lagrangian filling. And what this does, it's 2 ways that are Hamiltonian not the same. So it's 2 ways to Lagrangian smooth. So you smooth in a way that you get a Lagrangian in a Lagrangian way smooth, a double point, so an inverse point. Now there are some conditions on these inverse points to do with the Maslov index. For now, every inverse point I'll consider satisfies this property. So let me first start in dimension 1. So what happens if our manifold M is exactly R? So here our symplectic manifold will be d star of M, so that's R2. And I'm going to do symplectic geometry in d star of R2. There are 2 Lagrangians in here. So this would be Q, this would be the coordinate P. And the first Lagrangian I'm going to have is literally the 0 section, which is P equals 0. So the first Lagrangian, drawing it here, that's L0, cut out by the equation P equals 0. Okay. Then there's the fiber, for instance, the potential fiber in the origin. That's this one. That's another Lagrangian, say, maybe just call it L1. And that's going to be P equals 0. And you see here in the middle, they intersect at a point. Say the origin is big enough. That's the intersect, and they intersect transversely. they have all the right conditions. And what you see in dimension one, and that's kind of pretty easy, is that this is the analog of the two-disk filling of the Hopf link. Like the right analog of the Hopf link in dimension one, well, the right analog of S1 is S0. So a knot in S1 is just a knot in the circle, it's just an embedding of 2 points. You can embed two S0s in two different ways. The 2 points here and the other 2 points far away, or you can interlace them. So I strongly recommend that you think of this Legendrian, which has two quote components. It's 2S0, so this one is 0, this is the other is 0. This is the Hopf link in very low dimension. So this is an immersed filling of the Hopf link. And now the claim is I can build two fillings of the Hopf link out of this information. And so the first thing that you do is that you smooth out in one direction. So if you think of this as being QP equals 0, you could do like QP equals 1, or QP equals epsilon, or you could do -1. So in one case, you're going to obtain a filling that looks like this. And in the other case, you're going to obtain the other hyperbola, or you're going to obtain the hyperbola which is this one. And these are operations which are relative to the boundary, and these two Lagrangian fillings are different from each other. So there's a Lagrangian filling L of the Hopf link, and there's a Lagrangian filling L prime, and L and L prime are not Hamiltonian isotopic to each other. So L is different. Does that make sense? So this is the operation in dimension one, which admittedly doesn't have much juice symplectically because everything is exact, everything is Lagrangian. So I'm not really saying these things. But it already illustrates an important aspect of this, which is you could have actually thought to go from here to here through this point if you were able to go from this picture to this picture. And very much in the same spirit as the standard handle in Morse theory, what's happening in here is that you have a disk. And this is a Lagrangian disk. I cannot emphasize enough, this is a Lagrangian disk. The number of times I see in papers the word holomorphic disk, when we should say Lagrangian disk, that has happened. So just be careful. This is a Lagrangian disk with boundary, another Lagrangian. Okay, this is a picture that maybe it's not completely common in Floor theory, but this is what the geometry is indicating you to do. And so if you find a Lagrangian L, in this case a filling, and inside you have a disk, V1, which is properly embedded on the complement of L, and it's embedded, then you can take this disk, it didn't matter if it was like a bit wobbly, you can just follow it until you contract this L down to this immersed one. And then what the statement says is now you could go and expand that in another way, which is going to give you some other disk B prime. Okay. So a piece of notation, given the data of L, this Lagrangian filling of the unknot, sorry, of the link on the top, and this disk. So this disk is the one disk that you need for that. We have an operation which is contract the disk and expand it in this way that produces another Lagrangian, which we're going to call mu sub d of L, and another disk which we're going to call mu sub d of D. And that is exactly, by definition, the D prime in this picture and the L prime in this picture. Does that make sense? So here the pictures really are legit and everything is exactly the way that I'm saying. So just so now when I say the extra data is, we're not just going to go hunting for Lagrangian fillings like this one-dimensional filling of the zero-dimensional Hopf link, but we're going to go hunting for Lagrangian fillings. Sorry, this is not no prime. Lagrangian fillings with this kind of passes in there. And that's a real fun problem in dimension 4. Not only do you have to now find Lagrangian surfaces in dimension 4, but you want them bounding with some cycles, bounding in Lagrangian disk on the complement in a set. Does that make sense so far?
Yeah, how did you know that these two Lagrangians, L and L prime, are not Hamiltonian isotopic?
Yeah.
Why are we doing this? Like, what exactly is the
So
goal here?
the goal is to produce as many fillings. And one way you can do that is by brute force. I compute like 27 of them. At some point you get tired, I got tired. And instead you say, let's do it very systematically. I'll just want one Lagrangian filling, but I will have a lot of disks in it. And this is this black person. Yeah, they're going to have a lot of disks in it. And then every Lagrangian disk filling that I will create will be through this procedure. It's a way of making it more systematic. Yeah. Even if you know that they're not Hamiltonian isotopic, there is information in knowing that they differ exactly by one such operation instead of like 2 or 3 or 4. There's kind of subtle information there. So Leonid Polterovich, and I rewrote his model in a different way in the notes than I in a graphical way. So in 1991, he stated and he explained how to do that in general dimension. So in general dimension, in particular two, what you have is the following picture. Is if you have a Lagrangian that looks like a sphere times r. So in this case, our Lagrangian is going to look like S1 times r, but this one could be n. And you find a disk. So this is the disk here, D. This is what he calls a Lagrangian handle. He calls it gamma in his paper. And you have such disk embedded inside of it. This is all happening inside of T star of Rn. In this case, T star of R2. There is an operation that goes and collapses this guy exactly to this red point in the middle. Now, this is going to be an immersed Lagrangian. And everything in here is happening in the exact setting. So this is exact to begin with. The process that deforms it stays exact. And then the other expansion, which you can go either way, is also exact. So I'm going to draw these in a different color. So this is some other guy. And it has some other disk. And I know it looks exactly the same. It's different. This is prime. And this is a different L. Prime. And now, all right. So very quick comments that are relevant to this situation. This operation from a smooth perspective does nothing. Namely, this is all happening relative to the boundary. And as smooth surfaces in R4 relative to the boundary, L prime is smoothly isotopic to L. In fact, a stronger statement holds, they are Lagrangian isotopic, not exact Lagrangian isotopic. So there is a way to say, I'm not going to go through an immersed point if you trade the exactness by non-exactness. So when the exact immersed gets traded by embedded non-exact. Exact immersed gets traded by non-exact, but embedded. And this is, if you're familiar with Lefschetz fibrations, this is the same reason why the Chekhanov and the Clifford tori are actually not Hamiltonian isotopic, but they are Lagrangian isotopic. And the reason is you would go through here by random momentum collapse, you would kind of go above it and then go on the other side in the Lefschetz fibration. So smoothly speaking, whenever you produce a new Lagrangian filling from one, smoothly the surface will be exactly the same. And the distinguishing feature is in Hamiltonian isotopic. That's the first important comment. The second important comment is this is an involutive operation. Namely, if I do to an L one of these Lagrangian disk surgeries and I arrive here, and now I take exactly the same disk that was produced out of this operation and do the Lagrangian disk surgery, you obtain another Lagrangian argument that you can do locally and you can prove it is relative to the boundary Hamiltonian isotopic to your L. So you actually just get two out of these options, not like, oh, I can start doing that so many times. One other way to think about this is why couldn't there have been a third way to deform these that we're now looking at? The statement that the Hopf link has exactly two Lagrangian fillings and not three is exactly the statement that this guy could only be deformed in two ways. So in a way, we now know that these really are the only two options. And there's no other way about this. Okay, questions on Lagrangian disk surgery?
How do you show that they're not Hamiltonian isotopic?
Well, they will typically not be Hamiltonian isotopic. That will depend on the circumstances. Classically, was first shown by counting holomorphic disks, but the sheaves are also going to be different. So either way, I don't do. Okay, so let me define this notion that I introduced. That I don't know. I like the name, but if somebody really has a better name, I'm open to that. So it's the notion of an L-compressing system. So what an L-compressing system is trying to do is exactly have as many options to do Lagrangian disk surgeries as possible. So L-compressing system. So let L be a Lagrangian filling of Lagrangian knot. Fill lambda. Lambda is good. This is a very general definition. In the notes I stated it can be any Weinstein manifold. You're looking for a relative Lagrangian skeleton. So you do this one, an L-compressing system for L is a collection of disks of this sort. So in the compressing system. Is a collection. And now I'm gonna call this, the compressing system is gonna have that one PD, and that's gonna be D1, some DS of disks, and these are Lagrangian disks. And you want to be able to do surgery in them. So you want them to be embedded. They're Lagrangian disks. DI is embedded in the complement of the Lagrangian. It's held properly embedded. And you want well, okay, for now, let's just say that. So that's an uncompressing system, period. So this collection is said to be maximal if it spans homology. So if you said maximal, this definition, it is maximal. And every example I'll give you in these lectures are going to be maximal, but there's some examples in the literature that are more interesting. So it is maximal if S equals the first Betti number of the Lagrangian. So the boundaries of the disk spin. So maybe I should if the boundaries of the PIs are a basis of the PIs close are a basis or on in particular S needs to be exactly one of them. Are we okay so far? So maybe the picture is for the 1,000 words here. So you have your Lagrangian filling in here. That's L, that's lambda at the boundary. And now an compressing system would exactly look like a collection of disks on the complement in R4 embedded. That could be D1. Then you would have another disk in here, maybe 2. Have another thing. I mean, there's different kind of disks. Job is whatever you can find. There is one. Does that make sense? Yeah, as I said, really what you're looking for is a relative Lagrangian skeleton that contains L. So this is, you have a wall, L has topology. You want to kill all the topology. So where you're thinking of the formula Weinstein structure in the 4-ball such that it retracts to exactly the skeleton.
So you call this a maximal collection. Is it clear you can't have more or you just don't care?
You can have more if you're not in the 4-ball.
Okay.
So you actually just can take kind of the Weinstein neighborhood of anything with many. And so for instance, if you take P2 and you take the central torus, the standard thing is 3 disks of that torus. And not only do there's 3 of them, but you know, because of I1 of the complement of a cubic in P2 is Z mod 3, they don't span either. Like, so is it, you know, you can have all sorts of kind of interesting combinations. So that's the picture. And the idea now, like with this picture, is here hope, start mutating. We call that operation mutating. So start doing Lagrangian surgeries forever and see what you get. Okay, so this goes south very fast. So the first thing is it's not obvious at all that if I do a Lagrangian surgery, I'm saying D2, what's happening to the rest of the people? And something interesting is happening, and tomorrow I'll talk more about it calmly. Essentially, what's happening is other people that intersected positively, its boundary, they suffer a dent twist. So there's some interesting smooth topology mapping class group happening where the people who intersect something positively are going to be affected by that. Now, when you start doing that, it might be that some of the disks becomes immersed. So some of the boundary points in applying this dent twist becomes immersed. And that is going to be problematic in that you're not going to be able to mutate further. So one of the things I'll talk about maybe tomorrow or Friday is about how you try to get around this kind of phenomenon. Okay, it's a smooth topology curves in surfaces problem, but it has a very significant impact on the trend. Is this sort of idea very clear so far? Because right now what I'm going to do is try to find these kinds of things for you or the trefoil, the Hovling, like things very explicitly.
But is it true that like maybe a counter example of the expectation that any 2 feelings will differ Like,
Yeah, so my conjecture is any two fillings of a lambda that are in the same. Okay. So you have that moduli M lambda. It has many components sometimes. M821, if you look at that, it has two irreducible components. That's why Paul Melvin and company, so that's 6 or whatever. So some of these knots have more than one irreducible component. The claim is, if you have two fillings and you look at the sheaves, any filling should be quantizable. Not first kind of conjecture. And second, once you have it quantized, you look at which component this point belongs to, and then the claim would be any two sheaves in the same component differ by the random structure. Because you can have things like M946, like two disks that are not even smoothly isotopic or something, and then that would violate that. But the point is, when you look at augmentation variety, we'll have sheaves moduli will have different residual components. And I would say within one, yeah, my conjecture is everything is randomly distributed. Yeah. Okay, good question. Ursula?
For fixed filling, how many uncompressive systems can you have? Like,
Yeah,
how
open
big
question.
is
So very, I mean, usually this, we've talked a lot about this. So, yeah, so there are a number of questions. The first one is, I could just ask, how many are there? Maybe I could get like different configurations. But even a more subtle question is, say I fix the boundaries. Could it be that there's a way to like take this locally? You cannot knot it by Leandro Polterovich, but maybe there's a way to like kind of knot it in a very interesting global way that we don't know either. And that everything here is sort of part of step 3. Step 3 is we gotta face the music of the nearby Lagrange conjecture for surfaces. It is ridiculous we don't know this for genus 2. It is ridiculous we don't know kind of how to classify Lagrangians and things that are like something like that. So any method that I could foresee like does prove that will involve essentially something that also works for nearby Lagrange conjecture. So that is a problem that, I mean, I can talk about it from the case of unknown because coupling, you do foliations by holomorphic curves. So those are methods that if you can generalize for higher genus or more situations where the virtual dimension doesn't give you that it's a foliation, then you're good to go. But yeah, it's kind of in the spirit of the same question. If two Lagrangians give you the same sheaf, are they Hamiltonian isotopic? And again, it's essentially nearby Lagrangian conjecture. And it's the first case of nearby that we don't know. Like it's like surfaces, genus 2 or genus 1 with a disk or 2. Those were the things. All right. Any questions on this? Okay, so now let's just to work out all these programs from the very beginning in the case of the trefoil, say. And again, the goal is to number 1, build fillings, number 2, quantize them, show that they're different, and then maybe now try to understand how all these fillings are related by this kind of Lagrangian disturbances. So I'm gonna do the trefoil worked out completely, and it will give me an opportunity to start introducing this thing called weaves. So I'm gonna give you the easiest examples of weaves that are nice diagrammatics to depict fillings that manipulate them. So as an example, consider what you have as stunning. So consider the lambda trefoil. That's exactly going to present it as 1, 2, 3, 4, 5. That -1 closure of that. By the way, quick, why are you not taking rainbow closure? This is very interesting. So I was taking rainbow closure and I was fine with rainbow closure. I had not been particular advocating for that. And then algebra people from cluster algebra started to ask me, oh, these moduli that you're getting for rainbow closures, they're very interesting. There's these positroid varieties, and then there's these kind of things related to the Grassmannian or things related to some interesting flag varieties. Like they started to see that and said, look, we do not know that the Richardson varieties, which are some intersections of sugar cells, are clustered, something like that. It's like, if you could do whatever you're doing for them, that would be great. But then you realize that you reverse engineer a Legendrian whose moduli is the variety they care about, and that is not a rainbow closure, but it is a -1 closure. So that's why I switched to -1 closures, because it contains more people, and not just more people, it's just the people that people in algebra cared about and didn't know. So the conjectures that I was able to address in algebra were exactly about those guys that you needed the -1 closure, couldn't do with rainbow. So it's not just capricious. It was a point. Richardson varieties were the point. So consider this thing, and let's try to find fillings. So let's build fillings. By using this d4 minus, the d4 minus move. And first, purely pictorially, what I'm going to do is to just think about these 5 crossings in here as 5 lines. And notice that it suffices for me to go down to 2 lines because then I'm down to the hop link. So now what I can do is, for instance, I can pinch the first 2 guys, and that will give me this kind of picture. It's telling me first pinch the next 2. Then I could pinch the next one in here, and then I could pinch a quick pinch. Then I could pinch another one in here, and then I'm down here, and you could just bring this guy down all the way, if you wish. And here you have the unlink. So this is the unlink. And this picture, at least diagrammatically, represents the filling of the puzzle. Okay, so what is this picture? Is it just the picture? No, it's not just the picture. It's something your eye sees in nature. So what's happening in here? So this kind of covordism, this so-called d4 minus covordism in here, is an exact Lagrangian covordism. So the Legendrian lift of the d4 minus covordism, so this is a d4 minus exact Lagrangian covordism, looks exactly like the following picture. So on one side, this is going to be a front in 3D. Okay, so on one side, it's going to look exactly like 2 crossings locally. So it's going to have this kind of 2 crossings in here. So that's one braid that we see in this side. Are we okay with this? And then on the other side, we're just going to have this picture in here and in here. Does that make sense? And now I'm going to connect this piece to this piece, and this one piece here goes to this guy. So that's good. Does that make sense? So the claim is, if you take the Lagrangian covordism that defines the d4 minus, and you take the Legendrian lift of that, that is a surface in R5. You can then project that down to R3, and it gives you a spatial front for the d4 minus covordism. The spatial front looks exactly like that, where each of these around here is like crossing, crossing, crossing. Does that make sense? One way that sometimes you can think about these things, and it's kind of like up to you, but you can think of it as this kind of. So think you have 2 sheets of paper. You physically pick 2 sheets of paper, like circularly, put them one on top of the other. Now, sew them like around here, or really like put some like big your fingers like that, and somebody else is helping you with the 3rd finger. And now go like blow in each of the ones, and you're gonna go right. So it's gonna be this kind of like pancake that has these like 3 pieces in here. So that's exactly what's happening locally around this one. It's called d4 minus similarity. All right. Okay, so you have this Legendrian lift, and so what I was saying the other day is, it's not that just for cakes I'm drawing these. This is literally the front seen from above. So this is the diagrammatics. This diagrammatics is the front of Legendrian lift of the covordism seen from above. Okay, let me make a comment here. This is my own personal experience, but at some point I started to think about one-dimensional like topology, like Lagrangian surfaces and everything. I used to work in higher dimensions, then I kind of went down to low. And it just stressed me a lot to think about surfaces in four things. It's just like, you can kind of visualize it in movies and everything. But then you realize if you're dealing with exact Lagrangian surfaces in a 4D case, you can always lift them to a 5D Legendrian surface in 5D, and then take a front for that. So now, what is the trade-off? The trade-off is now your eyes see something. This is a palpable wavefront that you can just go and touch and play with. The trade-off, though, is now you're in dimension 3, which is better than 4, but you now have singularities. To me, there was no doubt. I'd rather learn, caustics and wavefronts from Arnold's book and master the singularity theory, but be able to touch it and manipulate it, rather than think about embedded. Embedded is just something my brain doesn't process. But singularities and rep chords, that's my deal. So that was my take on that. I prefer visual things, even if they're simple. Yeah. So now you can also do computations much easier like that. And so you have this candidate in here, and in general, you're going to have other people. So this is the first filling, L1. And now you're going to have other fillings, L2. So what's a possible other filling that you have? It's like, well, you again draw 5 people in here and go, well, first I'm going to do now the first 2, and maybe I do this one afterwards, then I do this one afterwards, and then I leave that like that. And then L3, you can say, well, maybe I'm going to do the same thing in here, but now instead of making the left one, I let it go with this one, and then I do this one, and I continue. Then I go like that. And then you have plus L4 plus L5. So in general, you get Catalan number because you're counting like trivial trees, binary trees coming for that. Okay, so hopefully this blackboard and the explanations are telling you now when you draw this picture, you're just not drawing pictures for kicks. You're drawing spatial fronts in 3D whose Lagrangian projections are embedded Lagrangian fillings. So these are the fillings, really you can see them and touch them if you just like stick in it and like thought of it as a front, kind of like that. It's kind of bubbles. Does that make sense? Okay, so you have these fillings, and now you want to start to distinguish them. So what do? You try to do shift theory, right? So that's what we're going to do. So quantize these fillings. So shift quantize these fillings would mean to find a shift. Now, can somebody guess, like in which manifold are we doing the shifts? You always do the shift in the manifold where you draw the front, right? So in here, we're drawing the front in R3, really R2 times R. So it's like J1 of R2 would be the manifold. So you're trying to look for shifts in R3 that actually have that as singular subscript. So now the important lemma here, the proposition, the local shift condition for that covariism, shift condition at D4 minus says the following. So I'm just going to draw a picture here. You have 2 people coming in, somebody coming out. Remember that there are 2 sheets in these models that I'm drawing in here. Is this picture all right? Everybody understands? So there's 2 sheets in here. So now I'm trying to draw a shift in R3 where the bottom, this is the bottom, down, and then the top is kind of up here, and there's 2 sheets in the middle, so there's 3 levels, right? Okay, so now, if you were exactly on top, so if you were exactly focusing yourself on kind of this end of this, how would you quantize this? Well, on the bottom down here, we have zero, k, and k squared, right? So if you think about it, on this side, that's exactly what I'm going to have. I'm going to have 0, k, and k squared. Now, everything is the same in this. On the other side, I'm going to have the same thing. 0 goes to k squared. This k squared is the same for everybody else. And this is the same as this one. 0, k, and k squared. So what I'm saying is all the k cubes being the same. So these, and these all being identified as being on top because the strata is conductible. The exothermy equivalence tells you that a constructible shift with respect to this stratification of R3 is given by the data of with this singular with the k shift, but it's 3 lines in K2. So these are 3 lines in K2. So 3 lines L1, L2, L3 instead of K2. And now what you want is such that, well, let's first look at the conditions away from this D4 minus singularity. The condition away from it is that this guy, this flag in here, is going to differ from this one exactly by a crossing, because that's exactly the crossing as we break. So as you go through here, you exactly see, as you go through this model over here, you exactly see one crossing, and like hopefully by now we're okay with that it's saying that this line must be different from that one. So what it's saying is L1 is different from L2, and now that's clearly there's a sigma 3 symmetry, so that's cyclic. So the condition is L2 is different from L3. And also L3 is different from L1. And that comes from a condition already away. So besides, is already away from the most singular point before minus, right? That's imposed already. And now the proposition is saying that's all, and that's it. Another way of saying this, I mean, what you actually prove is the d4 minus point doesn't give you an extra condition. So I has no extra constraint. So if you're a sheaf satisfying this thing, that is to say the singular support here, here, and here, then actually the singular support here is exactly going to be the downwards direction. So that's sort of the technical proposition. You could imagine yourself proving that, right? Like you would take this pretty now elaborate pose set from all the arrows and everything, is like a one-dimensional high-up version of the crossing conditions. You know, 3 crossings, and this whole thing is going to go to another one. And now you start to compute all the microstock maps, and well, this map was an ISO, this map was an ISO. And it happens that you just like complete the whole diagram without ever using the d4 minus. So you're good to go. Okay. I mean, that's the way it goes. For conceptual comment, this is actually the front of a complex cusp. So you know how you usually do like J1 of R, like in R3 with the standard context structure being real? Nothing stops you from doing holomorphic contact geometry. So you can think about J1 of C, and that's capturing holomorphic maps from C to C with their first derivatives. And you can draw fronts. So in particular, you can draw the equation z squared equals w cubed. And that gives you an holomorphic Legendrian whose thing is now an holomorphic cusp. So now you can take the real part of it, and that gives you a front in 3D. What is it? It's this one. Now, why is that useful? Why is it useful to use things that come from holomorphic geometry? And that was kind of one of the initial motivations. A cusp in holomorphic geometry gives a singular point which is holomorphic. Therefore, is of complex dimension 1 less. It's of complex dimension 1. Therefore, any real front that comes as the real part of an holomorphic front will have front singularities of codimension real 2. It doesn't tell you what's happening here. The crossings are not real singularities. So the only singularity here is 1 point in a surface that is highly non-generic, but it's extremely useful. Because now I don't have to draw swallowtails and everything. Are there swallowtails? Yeah, there's 3 swallowtails in here, but they're all kind of side. They're kind of philosophically why conceptually, because they come from a complex singularity. So that's one way to. Okay, good. So this is a local condition against. So therefore, so a corollary of this condition is all fillings felt from using d4 minus singularities and Legendrian isotopies in between can be quantized, or sheaf quantized, and not just that, it's very explicit. Sheaf quantized, and the problem still is a problem about lines and planes, so on and so forth. So let's do this explicit in this application. So what do I have here? The initial data that I have is a line here, L1, a line here, L2, L3, L4, L5, and then the next line in here is going to be the same one. So that's L1. Are we comfortable with that? Okay, so the conditions that the lines must satisfy up in here are exactly the conditions that cut out this moduli space M of lambda, right? I mean, model the quotient. I'm going to ignore the quotient for a second, but it will be the variety x beta. All right. So now what's happening? The beauty of these is that these fillings, through this particular computation, cut out a subspace of this moduli. So L1 gives via its quantization, so via its quantization, shift quantization f of L1 constraints that you can impose, and therefore a subset, maybe let me call this subset T of L1 inside of my modular space. Does that make sense? So let's work out this very explicitly. So let's start here. These lines L1 and L2 are different. There's already up there. L2 and L3 are different. Nowhere in the modelized space there's a constraint that says that L1 should not be L3. There are points where L1 is L3, and there are points where it's not. Yeah. When I start sweeping this around, what the shift quantization condition around these points tells me is that L2 should be transversed to L3, I had that. L1 needs to be transversed to L2, I had that. So the extra condition that I'm gaining here is that now this is saying, do not look at everybody in this model I, impose the condition L1 is different from L3. And that is an open condition. And now I can continue. Now I go down, and now I perform a D4 minus. Whatever Lagrangian covariism I've obtained is such that it's imposing, isn't that great? Just like you look at the picture and it's obvious. L1 should be different from L4. You don't need to like compute anything. Or different from L4. And then you have the final one that's going to be L1 different from L5 that actually you already needed. So I mean it says these which we knew. So. But for instance, this set is now a set that you can name very explicitly. This is a subset of these moduli cut out by the conditions L1 different from L3 and L1 different from L4. And now, if you're patient with matrices and ZI coordinates, you can write, as from Hao has done in the case of the trefoil, you can go and write down all these conditions in terms of Z1s and Z2s and Z3s and so on. So, you know, now, why is T? So the T is because this isn't just any subset. This subset is isomorphic to an open torus. Again, mind you the quotient, so you have to quotient everything by the right thing. But it's like this modulo will be the T action, but it's going to be an open torus in X. So maybe I should have written more legally. But this is like X of beta, and then remember that this space is this one quotient. So again, a torus. Does anybody have a sense of why that's true? Okay, so what happened every time we pass from here to here? What happened when we impose the shift condition from there to there? Well, here I have some choice of flag. So L2 is something different from L1. That's no constraint. But now I get L3. So now question, what is the space of lines like in relation to L1? So you know that the line L3 cannot be L2. Wait, do we agree that the set of lines in the plane is P1, right? So, but now you are not allowed to be L2, right? So locally, you already have a choice of C for that, the complement of a point in P1. And now these extra conditions imposing that L3 is not allowed to be L1. So this condition in here is a C star worth of choices. Where have we seen this C star? Yesterday? When you unstock?
Local systems.
This is accounting for the local systems for the saddle covariism. So if you think of like Yupan's paper on 2 torus knots, when you have a saddle covariism, you have this arc kind of flowing down. That's this relative homology class, the local system relative to that. So that's the C star choice in there. Does that make sense? So again, the punchline of this is not every point does extend inside, nor it should, but the set of points that do extend inside, it's exactly going to be of the form C star to the something, because each condition is open, it's going to be an open torus chart. So that's how we got this filling out of that. And now, how do you intrinsically talk about this open torus chart? This open torus chart equals what? How should I be naming this intrinsically? This is local systems, GL1C of who?
L1.
Of L1. AKA, as I said before, H1 of L with coefficient in GL1C, so that's this thing. So that's a very explicit realization of that torus. I mean, we computed in coordinates kind of why it had to be a torus, but I mean, it had to be whatever it is. Okay, so now, I mean, we can keep having fun with this, but for instance, for L2, what would I have? Well, L2 is going to give me some other torus, T sub L2 inside of my variety, X beta. How is it cut out? Well, here, the first equation that I get in there is that L2 is different from L4. And down here, I get the condition, and in here, I get the condition that L1 is different from L4. Do you see that? And so now it's going to be some other torus in here. And maybe in this explicit example, it's completely apparent that this torus is different than this torus, which implies that this shift quantization is different than this shift quantization. which implies that these two objects, L1 and L2, are not Hamiltonian isotopic, because the sheaves are not isomorphic. If the sheaves were isomorphic, these two guys would have been the same. So, okay, just to pause for a second. What the torus is doing geometrically, it's not that a Lagrangian filling gives you a torus. It's a Lagrangian filling with a local system gives you a point in the torus. And a Lagrangian filling with all the possible local systems gives you the torus chart. Now, these are torus charts in, an algebraic variety. So if this is your algebraic variety, you have here, whatever, T of L2, and then you have T of L1 in there, T of L1. This is not saying that these some people don't talk to each other. These are both Zariski open sets. They're both dense. There's tons of people in the intersection. So what is the interpretation of this? Well, it's kind of up to you, right? It could be thought of as L1 with a certain local system, or it could be thought as L2 with another certain local system, okay? But what makes them different is that the total set of local systems, you let them vary, that complete set differs from this one to this one. And that's what allows you to show they're not Hamiltonian. Is that point clear? The charts as open charts are different. The fact that there's point in the middle, you guys' interpretation. But that's why I always talk about charts, not of points, because it's not that you can say, oh, this point is this Lagrangian field. It's not like that. It's more like the chart, specific to a chart is that. Okay. Does that make sense so far? Okay, so now you can tell me, let's see if I'm explaining things clearly enough. Now we find a bunch of Lagrangian fillings. Here we have them, but maybe we wanted to get from these ones, starting with these ones and performing Lagrangian surgeries. So the task was not just to find a Lagrangian filling, but find a Lagrangian filling without compressing local systems. So this is the last comment. Blackboard is how do we find compressing local systems in this situation? And that's the theorem that, 100 something pages later, you could use in n strengths. But really understanding well in 2 strengths is it's like 50% of the job. Okay, so let's think about it this way. So how to find L compressing systems? Now, one nice thing about the front is that I need to find a Lagrangian thing, which you can also think as finding a Legendre thing. And the beauty of the front is that whatever you draw is a Legendre. Wait, you're always kind of in the 0 section. You cannot go wrong and draw something that is like simplex. I mean, it can, but it will be a blob. So if you draw like a plane or something like that, no. Okay, so how do you find that? So the observation is the following: is locally around P4 minus, there is an ascending and an ascending manifold. So we can, of this saddle cobordism, so we can think this way. And now let's look at the topology of this. So topologically, this is a disk. Like the Legendre lift of this is the disk, which is a 2-sheeted branch cover of the disk. So purely smoothly, what's happening is that I have these 2 disks essentially mapping with like z squared, the z square map going to there. So now, well, what does that mean? It means the preimage of this point being the branch point is 1 point. But now the preimage of any point outside is 1 point. But here, what am I going to see? Well, here I have exactly 2 branches cutting. So I'm going to have one lift that comes from this branch and another lift that comes from the other branch. So above this guy, above any of these guys, there's actually 2 points. You see, above any of these guys, above here, there's 1 point and another one. One from one branch and one from the other. So, and this is very much in the spirit of like Donaldson's matching path and everything for vanishing cycles. What you can draw in here is a lift of this guy, and the lift of this lifts to an arc. That kind of looks like that. Like kind of looks like an arc that goes down this way. Does that make sense? Now, it doesn't just lift to an arc, it lifts to an arc in a way that I can fill what's in between. And that's going to be this piece in between Lagrangian. Why is it Lagrangian? Well, that's the beauty of the front. If you draw it there vertically, it's gotta be a Lagrangian. It's the same as a Lagrangian fiber. Essentially like a tangent fibers in here, ding, 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 ding. So therefore, if you see something like that, some move done in here, and then I go down, and I see a move somewhere else. What is this? Well, I can start my disk, so I can take this edge of this trivalent graph, think of it as being the target, the codomain of the branch cover, lift it upstairs, and so what does a segment between two branch points with the same ramification lift to? That's just this is kind of Rolson or whatever you learn this stuff. That lifts to a circle, right? So it lifts the circle as one, and that circle as bounds, leaves something like that, and this guy bounds a Lagrangian disk, a Lagrangian embedded Lagrangian disk.
When you shift the two green curves off the red curve, are they like both on the bottom?
Well, I
shape or both
didn't.
on the upper?
The answer is this is meant to be like literally on top of it, like they didn't shift them. If I wanted to really, okay, that's a good point. So if I really wanted to see this guy in here with a perturbation, I would shift the curve like that. And then it would be top, bottom, top, bottom. But I would have to shift it to sort of pass the branch points. Does that make sense? Like you see, like you're starting here on the top sheet, go down to the bottom sheet, go back to the top sheet, go up to the bottom sheet, and then you close it up. Okay, if you perturb it for minor singularities with the swallowtails and everything, I can actually show you the Lagrangian disk very explicitly. It's like a very nice picture. Very kind of see there. So that's how you get an all-compressing system. Every time you see an edge here, for instance, if you take this L2 filling here, this is a Lagrangian disk, and this is another Lagrangian disk. For instance, here you're going to have one all-compressing system coming from this guy, and the other one is going to come from this guy. So any of these guys for 2 n torus knots, you now know, after this lecture, you should be able to say, for 2 n torus knots, I know how to build many fillings, and not just many fillings, without compressing systems. Okay? But really, when you go up in strengths and everything, you don't want to build many. You just want to build one with a non-compressing system, and then just start mutating. So then the last thing in this lecture should be what? Should be me explaining how Lagrangian disk surgery at the beginning of the lecture looks like in this picture, okay, the middle of the picture. So then the result, the proposition theorem, nice thing. I mean, you're dealing with trivalent graphs, and sort of what else could it happen? But this surgery, your weaves, let's call this kind of diagrams weaves for now. Your weaves, it says that the way to mutate, you start with the Lagrangian disk, which is presented in this way to you. And this is the Lagrangian, this is L. So this represents the Lagrangian filling L. Now you have the disk that lives above here, D. So if you're in this situation, your Lagrangian filling comes from this picture, the Lagrangian projection of the Lagrangian lift of this front in R3 with this particular disk, then mutating that guy doing the Lagrangian disk surgery is exactly going to be sometimes called the Whitehead move. So here you collapse and you will expand exactly the other way. It's going to be given probably. The other option. This is a move relative to the boundary, and this is the new disk in here. This is your disk D prime in here, and this is your new Newtonian. Does that make sense? And now should be a nice exercise. For instance, for 2 n torus knots, we have these trivalent vertices, so there's trivalent graphs with a bunch of spokes at the end. You can go between any trivalent graph to any other trivalent graph by doing this move. So you actually see very explicitly how the scalar number of words of fillings for 2 n torus knots, you could just have obtained them by having one and it's starting to mutate again and again. For instance, if you take this guy over here and you mutate on the first two guys, then you're going to have this trend ending in here. That's exactly like this kind of first condition up here, like the one this kind of start. Okay. And then you can keep doing that. So first you mutate at, say, at the green, then you mutate at the red, then you can mutate back at the green. But if you have a more elaborate configuration of disks, as long as you know you can keep mutating, you're going to get many Lagrangian fillings. And one punchline is, by now, we know many examples, infinitely many classes of examples, for which you produce infinitely many feelings that way. And it's not just infinitely many feelings, it's like they have a particular kind of structure to them. They have like a certain, it's not just a set, which is infinite. They're very organized in a certain way, and that's what relates to the so-called cluster exchange graph, so on and so forth. Okay, are there any questions on these examples for two strands? So these are Lagrangian surgeries, now realized visually for these Lagrangian systems, Lagrangian fillings via compressive systems. And this is kind of all the justification of why the sheaves played well here with them. Okay, so then tomorrow, 3 strands, 4 strands, more general statements, and eventually down the road, we'll have a conjecture about what the answers are in general. Good? Okay, let's all have lunch.